following this successful demonstration that Hawking's prediction was correct, were there any other experiments that followed it? And what were the advantages of those experiments that followed your initial one?
So various other, people had, Ralph and I, for example, showed that in a waveguide one could get the same kind of effect. And we suggested sending a strong wave down it and having capacitors that were nonlinear capacitors, which could again form horizons and so forth. And then Ulf Leonhardt and people had argued that one could do that in an ordinary optical fiber, and suggested using ordinary optical fibers in order to do the experiment, and they did some preliminary experiments with that. There was a group with Daniel Faccio who used ultra-intense lasers in a block of glass, of silicon dioxide basically. And the nonlinearities in that were such that could also produce a horizon in which, and they argued that they had seen something that could be the analog of Hawking radiation in there. The problem was that the intensities they needed were such that if you cranked up the intensity only a little bit, you could actually see the track left behind in the glass by this very, very intense laser beam having etched its way through the glass. And so, I still don't know what it was that they saw. And it's still possible that they saw, if you will, a quantum effect. On the other hand, it's doubtful, and I think even they are, shall we say, there is doubt as to whether or not that's what they've seen. So there were a number of attempts around, starting in around 2000, 2005, to see these kinds of effects in a variety of systems. It was at that same time that Jeff Steinhauer in Israel began being interested in effect, in his case using a Bose-Einstein condensate, which has the huge advantage of being cold. So, temperatures, I remember giving a talk in the late 1990s, and one of the Raisin from Texas, who's a Bose-Einstein condensate physicist, was in the audience, and I said, you might get a temperature of 10 to the minus 12 degrees, but that's obviously, it's not going to get done. And Mark Raisin put up his hand at the end, and he says, I think I could do 10 to the minus 11 even now. Which just blew my mind that these experiments would actually be done. And, so Jeff Steinhauer has, over the course of about 15 years, kept developing his system. One of the advantages of a Bose-Einstein condensate is the velocity of sound is very, very slow. So making a waterfall that is the same velocity, this is millimeters per second, it's not hard to move something at millimeters per second. It has the huge disadvantages that it's tiny. So, his biggest ones are sort of 1/10 of a millimeter. So you're doing this experiment on this very, very, very tiny little droplet of fluid, if you will, which makes it hard. So there were a whole bunch of groups at that time that were interested in doing exactly experiments like this. And, the same thing has continued. More and more people are interested in carrying out experiments like this. It's hard to think of, you know, other cases where one can do an experiment. Well, as after one of my colloquium in which I talked about our experiment, one of the people in the audience put up his hand and says, "Do you mean to say you think that maybe in 10 or 15 years we could have an undergraduate experiment in the lab in which the students are doing something having to do with black hole quantum mechanics?" Sure, and you know, there's few experiments which you know are related to stuff that is so right at the forefront of physics that you could imagine carrying out the experiment just on a tabletop for a minimal amount of money. So I think that's gotten a lot of people interested in doing it. You know, if an experiment takes you 20 years to do, it's hard to get undergraduate or graduate students to work on it because, you know, one of the few examples I can think of is you know, the LIGO, the gravity wave experiment, where that was sort of a 40-year experiment where there was absolutely nothing for 35 of those years. Well, it was actually longer than 40 years. More like 50, well, now 60-year-long experiment, where for the first 55 years nobody saw anything, and then suddenly were completely deluged by data that the experiment is producing. And it's one of the few cases where one could do that. But certainly I could never be involved in an experiment with, you know, 5,000 other people all working on the experiment at the same time.
So finally, coming back to the Unruh effect then, you mentioned that one of the benefits of working with a Bose-Einstein condensate is the low speed of sound.
Right.
So could you therefore set up an experiment to detect the circular Unruh effect and exploit the fact that the speed of sound in the system is much less?
Yeah, so in a sense, taking Bell and Linnaeus's idea over the past, what is it now, almost 5 years, I guess, there's a group here at Nottingham, me at UBC and also at Texas A&M now as well, people in Vienna, etc., have come up with this idea of doing, again, an analog kind of experiment in which instead of, you know, using light or using storage rings and so forth, one has a BEC, a sort of a BEC in a little dinner plate, and instead of hauling a little detector around like a spin of an electron or something, which is very hard to accelerate, instead putting in a laser spot on it and using the fact that these quantum fluctuations in the BEC, one of their side effects is to change the index of refraction of the BEC. So when you shine the laser beam through it, they get very, very slightly delayed in time or advanced in time depending on exactly what the density was. So you can measure the density of the BEC. And all of this occurred because Silica, who is now at Nottingham, held a small conference, a workshop basically, where the question was, you know, are there things that we could do in order to see some of these effects, who knows what? And Georg Schmidtmeyer came up to me and said, afterwards in the hallway, and said, could we use, you know, lasers and BEC to see this thing? And I had done a whole bunch of work, both on LIGO, the quantum mechanics of LIGO, and you know, quantum mechanics, if you will, of laser oscillators and of laser beams and so forth, many years ago. And I said, sure you could. And it took us another 3 years to make that sure into sure. Because mine was based purely on my intuition and on my past work and so forth. And the group managed to show that, yes, if one pushes all of the technology, sort of things which people have done, but not all at the same time, and we managed to achieve all of them at the same time in the same system, that it looked like it would work. And this is an attempt to measure this acceleration effect now in the circular case. The circular case has many advantages. The first, as you mentioned, being that with linear acceleration, you rapidly fly far beyond your laboratory, unless your laboratory is the size of the solar system or something, which few funding agencies would be willing to build an accelerator that size. Whereas this thing stays in the lab. The second thing is, as I mentioned in the linear one, it's the time dilation, Einstein's time dilation, the change in time of a moving body. That's a crucial feature of seeing this thermal radiation. In the circular one, the particle is always going at the same velocity. So its direction keeps changing, but its actual velocity is the same. And as a result, you don't have to worry about this time dilation. It's the same no matter where you look at it. And that makes the experiment much easier. So there are many, many reasons why that experiment, that circular experiment, is much easier. And the hope is that over the next few years, using Jörg Schmidtmeyer's absolutely incomparable knowledge and experimental abilities with Bose-Einstein condensates and my theory and Silke and her group's work on experiments and all kinds of different analog models, which this would be another one of. Maybe we'll get it working. It's going to be non-trivial, but I don't think it will take as long as LIGO. I sure hope not, because I won't last that long.
So just to wrap up then, it would be cool to get some comment from you about, you mentioned the power of these analogues for studying effects potentially at the level of undergraduate physics within a relatively short time scale. You can do these experiments on a time scale less than 40 years. What do you see as the potential of these analogues moving forwards?
What is the
potential of these analogues moving forwards in terms of their discovery potential?
Well, I think the key thing they do is to give one, because any analog is not exactly the same as the thing it's supposed to be an analog for. And that can get very dangerous, because the tendency of people is to say, okay, A is similar to B in this area, therefore A is the same as B in all areas, which clearly is a false logical move. But in a sense, it's that difference that also is part of the strength of analogs. Because one is unclear as to what exactly it is, for example, in the case of the particles, what is creating these particles? Where do they come from? And we really still don't have a good answer. We have sort of pieces of an answer, but not a good answer for that. Seeing whether or not one of these analogs, which is like either the acceleration radiation or the Hawking process or whatever, is very similar in certain regimes, but is very different in other regimes. As I mentioned with the Hawking one, as you get to high frequencies, it behaves very differently to the thing that you would get around black holes. And to realize that the effect that you're looking for is still valid tells you that those areas in which the two differ are not important for the effect. And so allows you to concentrate on those parts that are similar. And where can you look at in those parts in order to really try and understand? And so it sort of acts as a way of pairing the fat from your steak so that you can, concentrate on the tasty muscle meat rather than this other stuff. Of course, Black Sprat's wife might disagree with you. But yeah, so I think that's one of the key things, and it also allows one to use some of those things like we've talked about. In the case of the black hole, etc. thing, at a certain point you get to the Planck scale. The Planck scale is a scale at which you expect quantum mechanics and relativity and gravity to be equally important. It's a length scale of about 10 to the minus 33 centimeters, 10 to the minus 44 seconds, a mass scale of about 10 to the minus 5 grams, an energy density scale of about 10 to the 95 joules per cubic meter, i.e. scales that in general we have not been able to look at or test at all. At that scale, you really don't expect to be able to understand anything anymore. We have no good theory for those kinds of regimes. And similarly, in these analogues, you have the regime in which the analogy really breaks down. For example, the atomic scale, where you really believe that the best description of a fluid is that it's made out of individual lumpy atoms, not a quantum field which has values everywhere, but it's here or there and so forth, made up of things like that. So the theory that one uses in order to predict things like the Hawking radiation in these analogues breaks down. Could one, by looking at those breakdowns in systems where we think we understand the fundamental physics, namely these fluids, give us a clue as to how one might be able to understand the gravity case? So I think that's another area in which, I think this could really provide us with insight. Many people say, look, these experiments, why do the experiment just simulated on a computer? The problem with simulations is that they tend not to surprise one. The advantage of experiments is that very often you do an experiment whose outcome is absolutely obvious, and for some reason, nature or God, Einstein, God does not play dice. Well, he was just wrong. The experiments showed that God does play dice. Experiments keep surprising us. And, these are areas in which the probability of being surprised is perhaps less. But I think there are still areas in which one really could be surprised, areas where we don't quite understand what's going on. Like this, how does the transition to explaining this thing in terms of atoms? How does one go from that to this quantum field theory is really still not well understood. and there could really be surprises in that kind of an area. So I think that's really worthwhile doing the experiments. And besides, it's nice, you know, making predictions as a theorist and then suddenly discover that, you know, God agrees with you. You know, many people believe that God agrees with them, but in this case, one is actually able to do experiments which show that it is really true.
I think that's a fantastic note to end on. Thank you very much for your time, Bill.
You're welcome.